Hello and welcome to this video where I'm going to explain the impact of the Raman effect on ultrashort optical pulses in nonlinear media. So let us get started. In a previous video, I derived this master equation which relates spatial changes in the electric field propagating through a medium to temporal changes in that field and to the response of the medium to the applied field. We saw that the nonlinear contribution to that response can be expressed as a triple convolution between a chi3 tensor and the electric field at 3 different times in the past. Now, that's quite a complicated formula, but it turns out that we can apply some simplifying approximations. For example, that the chi3 tensor is actually just a scalar, and also that we can look at the envelope of the electric field rather than the actual electric field. Using those tricks and also some other ones, we can eventually derive the general nonlinear Schrodinger equation. And this equation relates the change in the field when going from one segment of the medium to the next to the amount of gain or possibly loss in that segment, the amount of dispersion, and the change in the refractive index of the medium due to a very strong field. Now, we also saw in previous videos that we can get both a sort of regular nonlinear phase shift that gives rise to self-phase modulation, cross-phase modulation, and four-way mixing. But we can also get something called the self-steepening term, which I also explained in a previous video. So anyway, today we're going to look more closely at this term right here and see how the time delay in the nonlinear response is going to give rise to the Raman effect. So if you look at this expression here, we can notice that it's a convolution between the power at different times in the past and some response function that tells us how much that previous power affects the nonlinearity right now. And to understand this, I think it's helpful to have a microscopic picture of how the glass crystal lattice responds to the applied electric field. So if we apply a very strong field at some initial time t0, we can see that the electrons will respond very quickly to that applied field because they're quite light. It's going to take a few attoseconds for them to shift around internally. And it's this very quick response to the applied field that gives rise to both the chi1 behavior, which is related to the regular refractive index, as well as to the chi3 behavior, which is related to the Kerr effect with self-phase modulation, cross-phase modulation, and so on. But what about the nuclei inside of this glass lattice? Because they're also charged particles that will respond both to the applied field, but also to the recently displaced electrons. It turns out that a few femtoseconds after the field has been applied, these nuclei will begin to respond and therefore shift around. And so that's going to give us an additional contribution to the polarization that depends on a time-delayed version of the applied electric field. It turns out that we can write the response function as the sum of two terms, where the first one is we can call it the instantaneous response of the electrons, and the second one is the delayed response of the nuclei. Now, I say instantaneous, which is not quite correct, but basically the electrons respond on a timescale that's very, very short compared to the optical pulses we usually deal with, that it's okay to model this simply as a delta function. And then we have to look into the expression for HR, which is then we can call it the Raman response of the molecular vibrations to the applied field. So once again, if we plug in this expression into the formula from before, we can see that we can just apply the convolution directly to the first term, which essentially gives us the regular Kerr effect that we've seen before. Now, this other term here, still we're convolving the power in the past with some kind of response function. And our goal right now is to figure out how exactly does this expression here look. By the way, I want to point out that we have this constant here called FR, which essentially tells us what percentage of the total nonlinearity is due to the Raman effect and what percentage is due to the usual Kerr effect right here. For silica media, such as optical fibers, this number is usually 0.18 or 18%. In other words, you can say that essentially 82% of the nonlinearity is due to the electron response right here, where around 18% is due to the Raman contribution. And this is just a parameter that you have to sort of figure out for every single medium of interest, but usually it's 0.18 for silica. Okay, so anyway, we have to figure out what HR looks like. And in other words, we have to figure out how we expect a molecular bond to behave when you apply a strong electric field to it. And one of my professors once had a really good observation about physics, namely that everything in nature is actually a harmonic oscillator if you just look closely enough. And it turns out that this is also a very good model for the response of the medium to an applied field. Essentially, we can model the behavior of these bonds as simple damped harmonic oscillators. So you can see we have a damping term right here and an oscillation term right here. And so they have different parameters here that are typical for silica. In this case, the loss time is going to be around 32 femtoseconds, and this vibration time is going to be 12.2 femtoseconds or something. It's going to, again, vary depending on the medium, but these are quite standard values for silica. So what does this function tell us? Well, essentially it tells us that the amount of nonlinearity a field experiences right now will depend very strongly on the power of the field that was present around 14.72 femtoseconds ago. Note that in this function here, we have to demand that the response function is 0 for negative times. And the basic reason here is that that we have to respect causality, because if we had a non-zero value for negative times, it would be possible for a power in the future to affect the amount of nonlinearity in the present, and that doesn't really make any sense. So that's a pretty strict requirement we have to obey. Another requirement, or that's more a matter of convenience, is that we normalize this whole function to a total area of 1, and that's just for computational simplicity. But to truly get a strong intuitive understanding of what's actually happening here and how this response function interacts with the power of the field, I've had to resort to one of the most powerful computational tools available to a modern physicist. I'm of course talking about the online graphing software Desmos. So let's take a look here. Now, in this diagram here, I've graphed a pulse as it would be detected using, for example, a photodiode and an oscilloscope. So the x-axis right here is simply the time, and the y-axis is just the amount of power inside of the pulse. So in this case, we have a kind of carefully chosen pulse, which has a very high peak power initially, that then drops off to 0 at later times. So again, in this diagram here, the x-axis is actual time, so everything to the left would correspond to the past, and everything to the right corresponds to the future. So initially we have no power, and then suddenly the power jumps to a high value, and then it begins to decrease back down to 0. Now I mentioned this because in the subsequent graphs, we're going to graph everything with the x-axis being the time delay. So everything's going to flip around, but just keep in mind that whenever you see the sharp peak right here, that corresponds to the front of the pulse, and the shallow end here corresponds to the back. Okay, so with that in mind, I've graphed both the same pulse as well as the Raman response function as a function of the time delay on the x-axis. And notice now that the pulse has been flipped around. So what are we seeing right here? Well, we're seeing that the total impact of the Raman effect on a particular part of the pulse that's exactly here at 0 will just be 0 initially. And the reason is that in the past, corresponding to all the areas over here, there's been no power present, so nothing has been able to excite these Raman vibrations yet, so nothing's really happening at the moment. But if we advance the time a little bit, for example to t equal to 0 right here, then we can see that this front part of the pulse is now beginning to excite Raman vibrations, but it's actually not really experiencing the impact of those vibrations yet, because even though the power is very high right now, it hasn't really had time to cause any vibrations, so nothing's really being affected at the moment. But if you advance the time just a little bit more, we can see that the convolution integral from before, corresponding to the area under the purple curve here, and again that's just the product of the blue function with the red power right here. If we integrate up all of that, we see that this part of the pulse actually gets quite a strong impact from the Raman effect. And if we increase it a little bit more, you can see it grows and grows and grows until a certain point here where it seems to peak. So again, the point here is that the amount of, let's say, Raman effect that this particular part of the field experiences, that depends on all the power that's affected the medium in the past. You also notice that if we keep increasing the time, the effect begins to saturate and even decrease, because after a certain duration, we can see that this front part of the pulse that excited the vibrations is sort of, we can see that part of the oscillation is beginning to contract now, and that's being counteracted by these more recent parts of the power that's trying to expand the molecular bonds again. So these two effects begin to counteract each other, which overall decreases the total Raman effect right now. And if we keep going, we can see that eventually we just hit 0, both because we can say the power in the past is beginning to have this sort of counteraction effect where they're working against each other, but also because the overall field here becomes quite weak. So the weaker the field is, the less the Raman effect actually applies. And at some point we can see it just hits 0. And if we advance a little bit more, we can see that the total area here is actually technically non-zero, which indicates that the Raman lattice is still like vibrating like so, but at the moment there's no field present for that vibration to affect. So again, nothing's really happening right now. And of course, if we keep increasing, just nothing really happens and all the oscillations begin to die out. I think we might actually be able to animate this, so let's take a look at that. So again, the front part of the pulse arrives and it begins to excite these Raman vibrations. That causes a big impact on this segment of the pulse, but as the pulse advances and dies down, these vibrations become less and less noticeable, and eventually the pulse is no longer there, even though the vibrations are present and slowly dying out. So I hope that sort of gives you a picture of how the Raman response function interacts with the power of a pulse at different times in the past. And of course I've also graphed this just for a Gaussian pulse, which is probably a bit more typical than this very contrived triangular one. So in this case we can also see that the front of the pulse is arriving here at a time of 0. So now the Raman vibrations begin to be excited and they're sort of being built up, and we can see that it's actually not at the peak of the pulse we get the strongest impact. It's actually a little bit after the peak that we get the strongest effect, marked here with the height of the purple dot. So you can see that it sort of peaks around here a little bit after the peak of the pulse. And again, that's to be expected, right? Because as I explained before, the whole Raman term tells us that we have a strong impact when the power was very high in the past. So we can move forward like this and see that it begins to die out as well. And I guess we can also play around with this and create like a square pulse, for example, and then see what happens if we make it a bit longer. We can see that we sort of increase and saturate like so, a bit like before, but sooner or later we sort of reach a steady state, at least for a very, very long pulse. Maybe we can make it a bit longer here just to highlight that effect. So we can see that after a very long time it just sort of settles in, because now there's been no change in the power recently, so all of this purple areas are completely saturated. Okay, so let's go back to the PowerPoint presentation for just a moment. So to recap what we've just learned here, we saw that, again, ignoring loss and dispersion, self-steepening and all those other effects, we have the Kerr term, which tells us that we get a big nonlinear phase shift if the power is very high right now. And then we have the Raman effect, which tells us that we get a big phase delay if the power was high around 14.7 femtoseconds ago, approximately at least. It depends a little bit on the shape of the pulse, but that's a general rule of thumb. So the question is, this effect here, what does it actually do to the pulse, and when is that impact going to be significant and large? To answer that, I think it's actually helpful to quickly review the impact of self-phase modulation on a pulse. So if we only look at the self-phase modulation term, we see that if we solve this equation, we find that the field at some further distance is just the initial field multiplied by a complex exponential that depends on the power envelope of the pulse. So for example, for a Gaussian pulse, we see that the field increases like this, and if we square that, we get the power, and that gives us the phase change marked here in gray. Now, the so-called chirp, or rather the instantaneous frequency of any given segment of this pulse, will be given by the negative derivative of this phase expression right here. And by the way, we use the negative because in the definition of the field, we're assuming that there are plane waves propagating in the z direction. So that requires us to have a negative right here. So we just need this negative in this location to cancel that out when we compute this derivative. But anyway, the point is that we get a redshift when the phase increases. So for example, here we can see the power is increasing. That means the phase is increasing. And if we take the derivative of an increasing phase, we get a negative value and a negative change in the frequency that corresponds to a redshift. And similarly for the back part here, we can see the phase is decreasing. So negative times negative gives positive. So we get a blue shift over here for the back part. If we actually compute it right here, once again, we see that the chirp will depend on the gradient. And if we actually map out that gradient for different parts of the pulse, we see that the front part experiences a red chirp, while the back part experiences a blue chirp. And at least for a symmetrical pulse, these will have the same magnitude and also affect parts of the pulse that have the same, we can say, local power. So in other words, if we have this kind of power peak, then the ordinary Kerr effect that we're used to leads to a symmetric broadening of the spectrum. Now that changes a little bit when we include the Raman effect. So if we look at a pulse like so, the phase shift will now be delayed by around 14.7 femtoseconds or so, give or take. And the point is that the formula for the chirp still applies the same way as before. So we get a change in the frequency when the change in the phase is very large. So now we have a big positive change right here and a big negative change right here. So if we graph out the two chirps, we can see that we have a high red chirp in a region where the pulse power is quite high and a blue chirp where it's not very high. So in other words, the Raman effect will lead to a preferential broadening towards the red side of the spectrum. And again, if we add together the Kerr effect and the Raman effect, we get a symmetric broadening plus a sort of biased broadening towards the red. So overall, we expect the presence of the Raman effect to shift the spectrum towards the red end. And again, the reason is just that we get this delay in when the peak of the phase arrives, and that also changes when the maximum gradient arises. And that changes where the red curve occurs, and that just is on top of the peak of the pulse. Okay, I have a few more comments about this expression before we move on. It's more of like mathematical curiosities, I suppose. But one thing we know is that the convolution of two functions is always the greatest if they are identical. So since this Raman response function contains this sine term that oscillates at around 13.1 terahertz, then we expect the interaction here to be the strongest when the power also varies at 13.1 terahertz. And this is another way of saying that we kind of saw that in a previous video I made about the Raman effect. But basically, if we have two frequencies that are separated by 13.1 terahertz, it'll be very easy to transfer power between them using the Raman effect. Furthermore, we have something called the convolution theorem, which essentially states that if you have two functions in the time domain, for example a and b, and you take the convolution, that's actually the same as multiplying the spectra together and then taking the inverse Fourier transform. Now that seems a little bit technical, but the point is that this expression here, once again, is a convolution between two functions. So we can either compute that correlation or the convolution directly in the time domain, or we can multiply their spectra together in the frequency domain. And so if we look at this response function in the time domain and compute their Fourier transforms, we get something like this, where the blue line here, that is the real part of this Fourier transform, and the orange part here is the imaginary part. And essentially, for the reason of some mathematical details, this orange curve here basically tells us that if we have some pulse with a center frequency here at 0, then that'll tend to basically steal power from any frequency that's 13.1 terahertz above, and it'll tend to donate power to any frequency that's 13.1 terahertz below. And that's part of what's used in so-called Raman amplifiers to transfer power from one pump into a signal that's 13 terahertz below. Okay, one final note here is that this response function I've presented so far is just an approximation to the real behavior of silica, which is a lot more, it's slightly more involved than what I've presented here. For example, this response function here isn't just a perfect damped harmonic oscillator. You might be able to see that it sort of doesn't quite have a large enough dip right here as you would expect, and it begins to die out slowly, but then also begins to sort of recover a little bit right here. So the point is that the actual vibration of the silica lattice isn't like a perfect damped harmonic oscillator. It has some other oscillation terms that also appear here in the imaginary part of the Fourier transform, or rather the gain spectrum. But overall, it's a pretty good model that sort of captures the essential physics of the lattice. So there's other models for different media, of course, and you can look into those, but we're going to proceed with just the one I showed earlier. But it's just to be aware that the story is a little bit more complicated usually. Anyway, I've also implemented the Raman effect in my own custom version of the split-step Fourier method that solves this generalized nonlinear Schrodinger equation. And so to test this out, I've conducted a little experiment here. First of all, I've defined a hyperbolic secant pulse with a 2 kilowatt peak power and a duration around 20 femtoseconds. That's kind of on the scale of the Raman response function. Then I've launched that pulse into two different simulations, or two different simulated fibers. In the first fiber, we have a negative group velocity dispersion. So this means that basically blue light will propagate faster than red light. And we have the nonlinearity turned on, but we have no self-steepening, and the Raman effect is just manually activated or deactivated right here. But for the second fiber, we have the same parameters, same negative group velocity dispersion, same nonlinearity, and no self-steepening, but the Raman effect is turned on. So if I propagate the same pulse through these two fibers, we can compare the output and then get an insight into what happens when a very intense, very short pulse is affected by the Raman effect inside of a medium. So let's try and compare their evolutions. So in this diagram to the left, we see the temporal evolution of the pulse if we propagate it through fiber number 1. And so if you watched my previous video on solitons, you'll notice that this is a classic second order soliton behavior, where initially we have a hyperbolic secant pulse that sort of squeezes into a big spike and then broadens out and then sort of oscillates back and forth like this as we propagate throughout the medium. So this becomes a little more interesting if we propagate it through the second fiber, where the Raman effect is also active. We notice that initially we also get something that looks a bit like the sort of oscillating soliton behavior from before, but part of the power seems to branch out and sort of move towards the right, towards later times here. And that's fairly easy to understand if we look at the spectra as well, because for the first fiber right here, we can see that the spectrum just remains symmetrical. But for the second fiber, we can see it begins to generally shift over here towards more red frequencies, or rather lower frequencies like so. So what does that tell us? Well, it tells us that the Raman effect is indeed, as predicted by the model, transferring power from blue frequencies towards the red ones. And of course, you can also look at this animation right here that I teased in the beginning of the video, where you can see that on top, we simply get this oscillating soliton behavior that we're familiar with. But in the diagram below, we can see that after this first initial spike of power, the transfer of power from the blue frequencies into the red ones gets so strong that this Raman soliton, as we could call it, sort of splits off from the main soliton and begins to drift further and further towards later times. And you can see that it sort of gets more and more red as we propagate forward. So again, kind of shows that the transfer of power from the red end, from the blue end towards the red, is indeed present. Now, I'm going to finish off with a few applications of the Raman effect. I mentioned earlier that it can be used for telecom amplification. That's quite a common technique. And we also saw that we can actually use it for continuously shifting the central frequency of a pulse that we're launching into a medium, which can be quite convenient for sort of, let's say, tuning the behavior. Finally, it can also be exploited for something called supercontinuum generation, which another YouTuber who goes by Desmos Lab has showed in detail. I'll link to that, his videos on that in the description. And don't forget to check out the full description for both links to the code I've used to simulate this and some other resources on the Raman effect. So anyway, thank you very much for watching, and I'll see you in the next one. Bye bye.